to indulge on the relationship between mathematics and physics, so I took the liberty to offer you a kind of talk. It's a very simple talk, but there is a part that is rooted in history and that struck me for novelty and interest, and is related once again by chance to Kelvin. So there is a part, historical part at the second third of my talk, second half of my talk about that. And I bet you will find it new, because as far as I know, has gone unnoticed. Okay, so the talk starts like this. I start from scratch. So Riemann's paper, 1857, solution to multivalued potentials, actually was part of his thesis on holomorphic functions. And Kelvin's correction to Green's first identity is actually what I want to stress. Then I go back. You see here, the first two themes are about the mathematics in physics and the physics in mathematics. And then the impact of topology in physics. Many of you know this Harnov-Bohm experiment or effect, and then the experiment that is just emphasizing the importance of topology in physics. And once again, I should mention a Russian, a famous man, a Fields medalist, Novikov. And when I ran into him many years ago, almost 20 years ago, he said, "Oh, Renzo, there is no doubt that topology is important for physics." And he mentioned this. And so I thought it was a good opportunity to revisit this. And then we go to modern time, application of multivalued gauge theory to the effect and conclusion and outlook. Okay, so I'll be very brief at the beginning, because most of you know the work of Riemann. So, you know, topology was, we can say that started with two papers, one by Euler on Königsberg Bridge, and that is regarded really as the origin of graph theory rather than topology, but certainly we can think of that as a paper, the beginning of topology, but certainly this paper is amazing. So the paper by Riemann was published in 1857, and they used to discuss about these things with Helmholtz almost every day at the time in Göttingen. Now there is a letter, a private letter now published by Betty, who met Riemann and communicated to another mathematician in Italy that the idea of simplifying multiply connected domains actually came from a discussion with Gauss. Remember, Riemann was not a student of Gauss. Gauss was chairing the selection committee for the position of Riemann. But of course, he was in great love of topology, as probably you know. He didn't publish anything except the famous formula that was not published, was written in a personal note. And the communication by Betty is very interesting. Gauss was thinking the way to distinguish a curve, a self-intersecting curve, the upper half from the bottom half, so to speak, of a plane that was crossing this curve at the intersection point. And so he gave the example of a coil, of a curve in space, making a coil, a helix, etc., etc. This is the report of Riemann to Betty, and Betty communicated this. So you see, Gauss is always there. Okay, little note to students, Riemann published only 11 papers. So if they tell you to publish a lot of papers, think first. And then publish a lot of paper with good ideas as this one. This is a paper is a 5-page long paper, and is very, very simple. The ideas are amazing, but the mathematics is just nothing. Okay, so the idea is to start the existence of what we call now an exact differential form. Say we have a scalar phi, and so we pretend that this is an exact form. And then what we do is that if we deal with this exact form, we have this condition, and I'm sure all of you can read this condition as if it were a third dimension of a curl operator, and that means that if we consider a closed curve, then by direct integration over this curve, we can show that that is 0. I know everybody can read this in terms of Stokes' circulation theorem, and so that's the version. Of course, we can shrink this curve to a point without any difficulty, and Riemann talks about 2D case, so we are in the 2D situation here. And then he says, okay, if you can shrink it to a point, then the region is simply connected. And in particular, you can establish this fact. Now, what about if there is an obstruction? This obstruction can be a hole in the surface or a pillar in a fluid flow of a bridge or something like that. And so what happens here? Well, we have at least one closed loop that cannot be shrunk to a point, and the region is therefore set to be doubly connected. So there is at least one curve, C0, where the circulation is different from 0. And the idea is to insert a cut. There are papers in not many papers in mathematics that use and apply analytical theory to consider this cut insertion and the reduction of a doubly connected or multiply connected domains to simply connected domains. But I will show you another approach that I find is extremely interesting, and is due to Kelvin. So this cut reduces a doubly connected region to a simply connected region, and let me emphasize this is just pictorial representation to open up this cut, okay? So actually the cut is unique, but I want to emphasize that the cut has two sides, Q plus and Q minus, and this is a little point, probably too trivial for Riemann to point it out. He doesn't say anything about that. But remember, we have two sides now for the cut. Okay, now, well, we can take our preferred example. I think I realized very late in life, not now, maybe 20 years ago, I was already pretty mature as a researcher. I just realized late that what we do at school, first year mathematics or high school, to say take a periodic function, consider 0 to pi or minus pi as your preferred interval, is doing this. We are cutting out this mod 2 pi and tell students to focus on in order to have single valued functions maybe, or even we know a farther reduced part if we want the trigonometric function to be invertible. Anyway, here is a function, tan minus 1. Gosh, I got in love with this function for lots of reasons that you already guessed probably. So I now insist on this function with my students, and I'll tell you why in a moment. So if we reduce this domain to single connectedness, then through a cut that I visualized here with the surface in green, then we reduce this multiplicity to simplicity if R is bounded by a curve. The cut insertion modifies the boundary. Okay, the boundary is now modified by this Q plus and Q minus. Please keep in mind that these two parts are the same cut. But we have to take account of the new boundary now. Okay, so this is in words more or less what Riemann wrote. An n plus 1 ply connected surface S is changed into an n ply connected surface S0 by the insertion of a cut of surface sigma that does not disconnect S. Here we are with the Kelvin. So we attribute Kelvin to the origin of classical topological field theory with this vortex atom theory. I won't tell you much about this. I'm sure all of you know this. And the idea is very interesting and genial. When people talk about Ed Witten, I met Witten a long time ago in Torino, and I mentioned this, and he was astonished to quantize energy by means of topology. I told him in 1985. So he is certainly the one who attributes correctly the origin of topological field theory to fluid mechanics. Now, it's interesting because many of us look at these old papers and sometimes only superficially. Let me show you what he had in mind. Well, he had in mind a microcosm full of these atoms thought of as vortex filaments. And then at a certain point, he said, okay, if I remove vorticity, then I have my microcosm full of tubes. And these really, he meant empty tubes. Interesting. And so I spent, not long ago, maybe a few years back, I wanted to go back with this and to see if he had anything else to say, and I was astonished. Here we go. The item 54 of his 1869 paper says that at a certain point we have a problem when functions involved have multiple values. And then he says that this calls for a serious correction. And what he meant, a correction of Green's theorem. So I'll show you what he had in mind. There are several pages, and here are condensated just in a few slides. So he immediately wanted to provide an example. And the example is the following. Imagine you have a cylinder infinitely long with a hole bored into it, the center on the central axis. So there is nothing here. It's totally void of fluid, etc. And then the fluid is in the light blue region. Okay, so if we have a hole, we consider this function again, tan minus 1 is multivalued, and suppose the velocity is given by grad psi as if it were a kinetic potential. Now, it happens that you can check is solenoidal and irrotational in W. Now, let's make this U a little bit more complicated, nothing terrible. Just put a phi in front of it so that we construct this field as given by two potentials, phi and psi. And then we apply the divergence theorem. So the volume, we equate the volume to the surface, and we get the Green's theorem. This is the form of Green's theorem when we apply the divergence theorem, and we can write it like this. Or, alternatively, by just swapping phi and psi in this form, is identical, of course, to this one. Then he asks himself, what happens is if one of these potentials, phi, is multivalued. Well, if phi is multivalued, you can compute, you can check that this quantity is 0. He does it for this specific example. So he just do the calculations. They are a bit long because you change a coordinate system, cylindrical, and then Cartesian, and then go back to cylindrical or polar. And then you can check that this is 0 and this is 0. Phi is multivalued. So when we take the grad, then the multivaluedness disappear. And so, of course, the Laplacian, etc. And by this, I mean the directional gradient along the nu being just the normal unit vector to the surface boundary. So this is okay. But then in this form, we have a problem if phi is single valued and the psi is multi-valued. If phi is single valued, then of course we have troubles. Here is 0. Okay, by using this function, you can check that the result of these two pieces is no longer 0, especially because we have no guarantee due to the multivaluedness of psi that this is exactly equal to the other one if we just put tan minus 1. So this is, he recognized that there's a general problem with Green's theorem. And he offers a solution. So let's go back to the example. He knew about, from Helmholtz, about Riemann's work. He couldn't read German, but Maxwell could read German, and Tate and so did. And so he asked Tate, his collaborator, to translate Helmholtz. He was taken by this. And then Riemann later. Later, these guys worked pretty fast. Later, 2 days later, and he understood Helmholtz in 10 days. And then he offered his theory a month later. We are December January 1869. Anyway, okay, so let's restore simple connectivity by inserting the cut surface sigma. And the new boundary is given by these two sides of sigma now, plus S. Okay, so if we compute this term, we can check that we have this term, okay, fine. And then we have this other term, and this is due to the fact that we have to consider the two sides contribution to the new boundary. So this 2 pi, where this 2 pi comes from? This 2 pi comes from the integration of a psi function, this one, calculated either at sigma minus or sigma plus. Sigma minus is like theta, okay? We compute theta, theta sigma minus is 0, theta at sigma plus is 2 pi. So we can interpret this as what he calls a kappa, very good choice, we know that. Because not only is a constant, but in his own words, he called it a circulatory constant. And he called this sigma, this surface cut, a circulation stopping barrier, very physical in his interpretation. I like to remark this because one reason I'll show you in a moment. Okay, so now all functions are uniquely defined, and we can write this, and then in the divergence form has this shape, and with this sigma plus or evaluation. Here is my words. So I just reworded his statement for a multiply connected manifold of Betti number G, number of holes, in the manifold, the volume V and boundary surface S. Green's first identity implies the reduction of M to simply connectivity, insertion G cut surfaces, and the corrected Green's first identity becomes this one. Of course, each surface cut has an associated constant. Now, first remark, we can interpret this as a liberal interpretation. So it's not due to Kelvin, but we can interpret this as a measure of the whole strength. So once again, we can quantify topology, if you allow me to say that, by the constant kappa. And remember, it's totally empty, this tube. And the second remark is that this approach, I think, went totally lost, but we can recover this technique in recent works in a number of fields. For us and this community, it's good to remember the work on helicity in multiply connected domains, and one of our participants here will surely talk about that. If M is like, say, a donut, then we have to correct helicity in order to have gauge invariance in multiply connected domains with this expression. Now notice this expression and compare it with that one. We can interpret this instead of circulation as a flux through cut surface, and then plus the contribution from the cut surface itself. So this is the work of David and, okay, David McTaggart and Valley. Okay, that was JFM, I think, David, 2019. Very interesting analogy. I want to go back to the influence of topology in physics. And so this is a well-known experiment, the Aharonov-Bohm experiment. I have to check my time. I think, okay. And, you know, the idea is to have a solenoid, and you have a current in the solenoid, and so that uses a magnetic field, and the magnetic field, suppose the solenoid is very long. In actual experiments, it's kind of a meter. So it's not that long, but it's enough to confine your magnetic field as a flux tube inside the solenoid. So we have magnetic field confined here, ideally entirely confined here. And in this space outside, the field is exactly 0. So this is the condition, curl of A being the vector potential. In steady condition, we have these kind of equations. And now, of course, circulation is given by this, and is non-zero due to the presence of the vector potential. So the idea of Aharonov and Bohm was published long time ago, and is the following. We have a flow of electrons that are sent from one side of the solenoid to the other side, And the electrons goes around there in a region where B is equal to 0. And they predicted that if you look at the potential and relate the potential to the flux, you probably can measure an interference pattern at the device in P. So very briefly, this is a sketch of a theoretical background. You have your flow of electrons following here. And you have to pay attention to the fact that first we considered a loop oriented in this fashion. Now, if we want to consider the split of the path, we have to consider the new orientation of C2. So we just go to the new parameterization of C2, and then we can do our calculations. Now, suppose we just change gauge to the potential. Of course, the governing equation is for psi, is a Schrödinger equation for electrons. And if you change the gauge, you have an extra phase factor in front of some background wave function psi 0. So we can consider this. The new phase factor, remember, has no physical observable effects, because the amplitudes of the background and the modified, the perturbed functions, the amplitudes are the same. Now, if the flow of electron is split in two parts, then we have to consider the contribution along C1 and the contribution along C2, eventually reversing orientation to C2 bar. Okay, this is the simple calculations. We have to consider the linear superposition of these two contributions. And then we sum and subtract for this term. And then when we go to consider this term, then we have to reverse orientation and finally get to this final result. This final result is expressed in terms of phi, which is the flux, the initial flux. So any change of flux is measured by an effect that is transferred to this superposition. Because any change of flux induces a change in the sum of the contributions, a change between final initial wave function amplitude and initial and final wave function amplitude can be detected. And that was from, you see the dates, from 59 onwards, people, well, not immediately as usual, but at a certain point, experimentalists start to work on that. And I ran in a group in France that were competing with the Japanese and other people all around the world to check if that was the correct thing. I remember, by the way, a very beautiful conference in Israel dedicated to Aharonov, I think Asher Yahalom and many other, Michael Barry and so many other, I'm sure was a great conference. Anyway, so this is the idea, to check the difference in amplitude, and indeed there is a difference, and this has been measured by interference device, and this is the work of Tonomura and PRL 86. So you see the propagation of electrons, etc., and then the shift in the device. Tonomura experiment provides conclusive evidence of the impact of topology in physics. Now we get towards the end of my talk. I've been pretty brief because I don't want to use your time too much. And the idea is, okay, we saw Kelvin's idea with the Hall, and then we saw this work on Aharonov-Bohm effect. What about now, today? So today, it's interesting because there is a kind of going back to the physical interpretation of cut surfaces. And one idea is, of course, much used now in the theory of this new state of matter, the condensed matter physics, that regards defects in what we call Bose-Einstein condensation. Okay, so the discovery of topological phases of matter is pretty recent, 2016, and as you all know, gave birth of a great amount of publications on these aspects. Remember, by defects, we think of nodal lines of a wave function. So, of course, geometric optics is there, as well as other fields. I stick to the condensates because the condensates admit an hydrodynamics interpretation due to Madelung and Bohm. We are 1927, and with Einstein and very few others, they were not very happy about this Copenhagen school of thinking, and the idea is, again, fascinating for students, I think, because the idea is, oh, we are not happy about that. We want a kind of deterministic approach to what we call now quantum field theory. And in order to have a deterministic approach, we can try to have, well, in this case, a hydrodynamic version of this approach. Now, remember, we are talking about a dilute gas of a very, very low temperature, millikelvins. And so this is a gas of, say, bosons. Bosons reminds you photons. Black hole, maybe? Okay. So this gas of bosons is not a fluid, okay? But if we apply the Madelung transform, we get equations that are very, very close to the classical equation of hydrodynamics. Well, the continuity equation for one, and then a sort of Navier-Stokes equation, because it's not exactly Navier-Stokes. The tensor in Navier-Stokes is in terms of the gradient of velocity, but here in the equation, the hydrodynamic form of a mean field equation called Gross-Pitayevsky equation involves actually gradients of density. Okay, but I don't want to show you this. There is a nice book, very accessible, by Viat, who presents this hydrodynamic interpretation. And here we have another thing that is very interesting for us. You know, 2005, we already have a direct numerical simulation of fluid flows at a rather advanced stage. So we have a descriptive interpretation of some kind of hydrodynamics on one stage, and the advances in direct numerical simulations that some people call trajectory approach in physics. And so streamlines, so to speak, or field lines that you can follow, etc. Remember, it's kind of virtual. I want to emphasize it's not really a fluid, but still you can think of this gas of bosons as a fluid. And so you can apply numerical techniques that just a day before you use for simulations of Navier-Stokes equation. The techniques are there, tools are there. So you can explore lots of features, as we will hear in the meeting as well. So the first thing is that we have a phase, a background wave function, let's call it chi, is your potential. If you like, is your kinetic potential. And then a velocity of virtual fluid. This is u in terms of this grad of chi. And what we have here? Oh, we have a sort of Kelvin's case study again. Why? We have a condensate, and then at a certain point, formation of defects. And these defects are whole, deprived of mass. There are no bosons, they are totally empty holes. And density goes there on the center of this hole. And so we can think of reducing this Kelvin's hole to really a very, very thin, almost a singular tube, if you like, in terms of Dirac function. And well, this is a nodal line of the wave function. So we identified the defect with a vortex line. Very well. But then, especially young people come to you and say, well, it's a vortex line. Very good. Okay. But then we have a problem. We have a problem in the definitions. Ambient space is now foliated by isophase surfaces, S associated with the wave function, all around the defect. But the defect makes your domain multiply connected. We know this now. So what we do? Well, chi is multiply connected. And there is circulation, nevertheless, quantized in this case, but There is circulation different from 0. However, the vorticity goes like 1 over r away from the defect, and the curl of u, i.e. vorticity, is 0 because grad chi is. So we have a kind of contradiction. We have vorticity, but actually it's not defined. And so I'm happy to tell you I spent a little time with Matteo Foresti and others, Simone and others, to study. Matteo actually guided me to study the book of Kleinert. I discovered that many theoretical physicists really love the work of Kleinert. Kleinert was a collaborator of Feynman. And I invited a number of people here, but they are, I'm afraid to say, I'm old, so they are too old. And Kleinert is still alive, as others. Keith Moffat is 87 now, Kleinert close to that. Michael Berry is taken by more serious stuff. Even Dennis Sullivan acknowledged this meeting as a good opportunity to talk about this. So I studied Kleinert's approach, and Kleinert's approach resembles very much Kelvin's approach. So you have a cross-section of your defect, and in this cross-section you consider a cut. Now this cut, you identify this cut with the isophase surface, and therefore the normal to this surface is the velocity, say u theta in this case. So take your preferred cut surface, and then you apply Kleiner's theory. So sigma is the locus. In Kleiner's approach and others, is a locus of a Dirac delta vector distribution. So it becomes, let me say, almost a physical surface, so to speak. A surface that is not only of mathematical value, but of physical value to do your computation. So the work, you apply Kleiner's multivalued gauge theory, and you come up with this correction to the velocity field, which involves now this Dirac delta function, gamma being the circulation, etc. And sigma only apparently plays a role here, is just a formal way to write this, because actually u does not depend on sigma at all. Okay, so if you do this and you interpret your cut surface as a locus of Dirac delta distributions in R3, for example, and this being just the surface integral, then you can show that the vorticity is now well defined in terms of delta functions, being the curl different from 0. And now this delta being interpreted as the curl of a scalar delta on the line, if you like. So this delta is just a delta distribution on the line, being t, the unit tangent to the defect. So if you keep going with this machinery, you make sense of a number of expressions that otherwise would be in conflict. And I thought this is a very interesting approach. Of course, it's not a typical, if you like, a functional analysis approach to multiply connected domains, but it reveals the role of physics to some extent that I find very intriguing. Okay, this is the last slide. Recent developments, application of Kleiner's multivalued gauge theory, distributional analysis to defect theory in geometric optics, superfluids, condensed matter physics, etc. That was actually condensed matter physics, the original motivation in Kleiner's book, and then he went on in other fields. Then we have the recent works that involve analog models in black hole theory. And this is, again, something that becomes simple if you followed more or less the hints I gave you. Well, you deal with bosons, photons, and these photons are localized. And now we have proof that black holes are rotational objects. So there is actually a vorticity that has been observed by indirect measurements. And so there is an approach to black hole theory using Bose-Einstein condensation. And of course, the impact on multiverse theory and string theory we'll hear about. And well, the significance is clear. Importance of multi-valued potential theory in modern mathematical physics. If you go back 50 years, you realize how little consideration was given to potentials. Physicists thought that was just a mathematical trick to help you out with the equations. But now we give potentials a physical meaning, and the development of a topological approach to the mathematical theory of natural phenomena is evident from recent advances in many fields of physics. The inspiration for mathematical treatment of singular behaviors in physical processes is something I cannot state that is underway, but in my mind at least is underway. We can now use techniques of cut surfaces and reduction to maybe treating the horrendous problem of singularity formation, for example, in reconnection processes, and the standard classical problem of finite time singularity formation. It would involve a new approach. And I think this is a very interesting idea for me and maybe for all of you. So thank you very much for your attention, and let's enjoy the meeting. Thank you very much.